According to physics, temperature is the average kinetic energy or energy of motion of atoms and molecules in a system. Therefore, the hotter something is, the higher temperature and kinetic energy it has because its atoms and molecules are moving around. It will be the opposite with absolute zero, because it is the temperature at which there is no molecular motion. Temperature has three main scales, which are Celsius, Fahrenheit, and Kelvin. Temperature scales. The Celsius scale has a freezing point of water at 0 degrees Celsius and a boiling point at 100 degrees Celsius. Its unit is the degree Celsius. On the Fahrenheit scale, the freezing point of water is at 32 degrees Fahrenheit and the boiling point is at 212 degrees Fahrenheit. The unit of temperature on this scale is the degree Fahrenheit. Kelvin is an absolute temperature scale defined to have a 0 Kelvin at the lowest possible temperature, called absolute zero. The official temperature unit on this scale is the Kelvin, which can be abbreviated K, and does not go with a degree sign. The freezing and boiling points of water are 273.15 Kelvin and 373.15 Kelvin, respectively. To go from Celsius to Fahrenheit, you have to put 9 over 5 times temperature in Celsius plus 32. To go from Fahrenheit to Celsius, you have to put 5 over 9 times temperature in Fahrenheit minus 32. To go from Celsius to Kelvin, you have to put temperature in Celsius plus 273. To go from Kelvin to Celsius, you have to put temperature in Kelvin minus 273. To go from Kelvin to Fahrenheit, you have to put 9 over 5 times temperature in Kelvin minus 273 plus 32. To go from Fahrenheit to Kelvin, you have to put 5 over 9 times temperature in Fahrenheit minus 32 plus 273.
Hi, Carl. So, first of all, I am going to explain to you two different concepts, heat and a specific heat capacity. So, first of all, heat is the energy that is transferred between different objects. It's important to highlight that the objects have different temperatures. Energy is always transferred from a higher temperature to a lower one. It is important for us to remember that all heat units can be converted to joules, the SI unit for energy. Now, I'm going to tell you some units of heat besides joules, right? So, there are calories, kilocalories, calories or dietary, British thermal unit, and therm. On the other hand, we have another concept. We have a specific heat capacity. So this is the quantity of heat required to change the temperature. This quantity of heat required to increase a unit of mass, a homogeneous material, 1 kilogram to 1 Celsius. This needs to be constant pressure and volume. We need to know that any substance has its own and unique specific heat capacity. This value will tell the temperature of the mass and if it's going to increase or if it's going to decrease. All of this is based on how much energy is added or removed to heat. So, the formula of finding a specific heat capacity is energy transferred heat over mass times change in temperature. Now, we have these two different bodies, a room temperature water and cold water in a cooler. Now, a question. What do you think would happen if we sink the bottle of water, of room temperature water, into cold water? So, the first object temperature that would increase, what do you think it's the one? Yes, it's the room temperature bottle water. And the cold water temperature will decrease. emphasizing the temperature of the bottle of water will increase and the cold water temperature will decrease. According to this process is a bit slow, but at the end, both final temperatures will be the same. All of this happens because energy is transferred from water bottle to cold water, since the water bottle's temperature is greater, right? It's hotter than the cold water's temperature. Therefore, this is why at the end, both of them have the same temperature. Thank you, Carl. Bye.
According to the zeroth law, when two objects are in thermal equilibrium and they add a third one, they will all be in equilibrium. Heat flows from hotter matter to cooler matter, reaching equilibrium, and it occurs when there is no net flow of heat. When they are in equilibrium, no heat flow will take place. The most common example of this law is when someone uses a thermometer. Since the body temperature will be transferred to the device, making the mercury expand on the tube, indicating both the body and the thermometer that are in thermal equilibrium, since they share the same temperature. The units used in this law are the known units of temperature, Celsius, Kelvin, and Fahrenheit. This can be mathematically interpreted as A equals B and B equals C, therefore A equals C. According to the first law of thermodynamics, or law of conservation of energy, it states that heat is a form of energy, and that heat cannot be created or destroyed. It can, however, be transferred from one location to another, and be converted to one form or another forms of energy. The equation is delta Q equals Q minus W, where delta Q is the change of internal energy, Q is the heat added to the system, and W is the work done by the system. This can be measured in joules, since it's the measure of energy, but the measure for thermodynamic energy is Kelvin.
Good morning, everyone. I'm going to explain you the thermodynamic processes and the first law. According to the first law of thermodynamics, which is the study of heat and work, it establishes that in each thermodynamic process there is a constant. Here we can see the first law of thermodynamics, which states that the change of internal energy equals the heat added to the system minus the work done by the system. Here we can see that all the thermodynamic processes and which is their constant. So I'm going to explain further each one of them and show you which one has their constant. So the isothermal process. The isothermal process, in order to happen, it has to be in contact to a heat reservoir, and its constant is temperature, as you can see it here. In the isovolumetric process, the constant is the volume. In their system, since the volume does not change, the work done is zero. Finally, the adiabatic process. The adiabatic process is when nothing happens in the system and it remains without letting heat in or out. Therefore, the thermodynamic processes have a straight connection with the first law of thermodynamics, establishing the constants of each of the processes. Thank you.
Hi, I come here to explain you the second law of thermodynamics. So first I'm going to tell you some about the theory about it. It describes the relationship between a thermal energy or heat and other forms of energy and how energy affects its matter. The second law of thermodynamics is about the quality of energy. It states that as energy is transferred or transformed, more and more and more of it is wasted. The second law also states that there is a natural tendency of any isolated system to degenerate into a more disordered state. So I found a statement of a professor of physics at the Missouri State University. His name is Arevalo Mitra. So he states the following. There are a number of ways to state the second law. He said, at a very microscopic level, it simply says that if you have a system that is isolated, any natural process in that system progresses in the direction of an increasing disorder or entropy of the system. So basically he states that any process that is made between two different levels can be called any type of second law of thermodynamics. So here I include an example. So here you can see a transfer of energy into hot temperature towards cold temperature, and that's exactly an example of thermodynamics theory. So to simplify it and tell you in some words, the thermodynamics is something that is any change or any transformation that happens between any heat or any forms of energy in any body. Thank you.